Hi there and welcome from Ventura, California to today's webinar, Mapping from UAVs, How to Optimize Accuracy and Efficiency Using GNSS Inertial Solutions, sponsored by Trimble applanix, Inside GNSS, and Inside Unmanned Systems, and hosted by WebAttract, the leader in thought leadership webinars. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session as our panelists discuss underlying concepts of georeferencing of UAV data using different methods and with practical examples from real-world UAV projects, a new UAV-based system for hyperspectral imaging, and direct georeferencing techniques using a multi-rotor UAV platform. You'll also have an opportunity to have your questions answered at midpoint and at the end of the presentation during the Ask the Experts panel session with all of our panelists. Now, we've invited you along with over 600 professionals from 58 countries across 29 states and provinces representing a variety of mapping technology interests. Over the next 90 minutes, regardless of your industry segment or your location, we're confident that you'll find today's webinar of value. Before we do get started, Richard Fisher, Director of Business Development at Inside GNSS, would like to take a moment to welcome you and introduce our main moderator and sponsor for today. Richard?
Thanks, Lori. On behalf of the Inside Unmanned Systems and Inside GNSS team, including Glenn Gibbons and myself, I extend a warm welcome to our international audience for today's web seminar. We're delighted you all could join us today. Our panel of experts will provide an introduction to mapping from UAVs and how to optimize accuracy and efficiency using GNSS inertial solutions. In a very short time, our panel of experts will take us from the theoretical to the very practical. And now I'd like to introduce our sponsor, Joe Hutton, who is the Director of Inertial Technology and Airborne Products at Trimble applanix. Joe?
Well, thank you, Richard. I'd first like to say how excited I am to take part in what I think is going to be a really, really exciting panel discussion today, and around a topic that's, of course, dear to my heart. Just a little bit about who we are and what we do before we get into the meat of things. Trimble applanix is a wholly owned subsidiary of Trimble Navigation Limited, and we specialize in providing enhanced productivity solutions using GNSS and inertial technology for various applications, including airborne mapping, seafloor mapping, mobile mapping, and autonomy. In the mid-1990s, Trimble applanix pioneered the use of using GNSS-aided inertial systems to directly georeference airborne mapping sensors on manned platforms, first with analog film cameras, and then with all digital sensors, including cameras, LiDARs, hyperspectral imagers, and synthetic aperture radar. Now, with the explosive growth of UAVs for mapping, we have pushed direct referencing solutions tailored specifically to the cost, performance, size, weight, and powers demanded by these platforms. The Trimble applanix products and solutions for direct referencing on UAVs are sold as part of the Trimble portfolio of products targeting UAVs. Trimble offers a complete range of OEM precise positioning solutions for the UAV industry, encompassing navigation, guidance, control, precision landing, and mapping and surveying. These products range from small, high-performance L1 RTK GNSS OEM boards all the way to multi-frequency, high-accuracy RTK boards and full GNSS-aided inertial solutions for guidance and control and direct referencing. We are very pleased to sponsor today's webinar focused on using GNSS-aided inertial for direct referencing of UAVs. And I want to thank everyone for spending the time to listen to our panel of experts today. I hope you find the talk rewarding and informative. Back to you, Richard.
Thanks so much, Joe. Appreciate that introduction. Now, I'd like to turn the webinar over to today's moderator, Demos Gebri Agzieber. Over the years, Demos has helped develop and moderate numerous Inside GNSS and Inside Unmanned Systems webinars, and he's especially close to today's topic. Demos is an associate professor of aerospace engineering and mechanics at the University of Minnesota Twin Cities campus. His research deals with the design of multi-sensor navigation and attitude determination systems for aerospace vehicles. Recently, Demos' work has focused on multi-sensor solutions for operations in GNSS stressed and GNSS denied environments, including the use of such systems on unmanned aerial vehicles. Demos, thank you for joining us again today, and we'll turn it over to you now. Thank you.
Thank you very much, Richard, and welcome everyone. Glad you could join us today for this exciting webinar. Before we get into the meat of today's topics, let's start with a quick poll to break the ice. So Lori, if you could bring up the poll question.
I'd be happy to. And folks on the screen, you should see that first poll question. And we'd like to hear from each of you. What type sensor payload are you interested in using for mapping applications from UAV? And choices here are RGB, infrared camera, LiDAR, multispectral camera, or hyperspectral camera. And, in this case, you're welcome to select all that apply. Looks like we have 60% saying RGB, 40% infrared camera, 72% LiDAR, 42% multispectral camera, and 31% hyperspectral camera. Any thoughts on those results, Demos?
A nice mix of different applications, and I'm pretty sure everyone is going to get something about the sensor they're interested in from today's webinar. So let's move on to introducing the panelists that are going to be talking about these things. All right, so our first panelist is Dr. Mohammed Mustafa. Dr. Mustafa has about 17 years, if not more, industrial experience in the field of geomatics internationally. He has authored or co-authored over 160 technical papers, technical publications, including some reference texts on the topic. He has served as the chair of the American Society of Photogrammetry and Remote Sensing Direct Georeferencing Committee from 2001 to 2010. And he received his degrees in a Bachelor of Science from Alexandria University in Egypt and a Master's and PhD in Geomatic Engineering from the University of Calgary in Canada. Mohammed, I'll turn it over to you.
Thanks, Demos, for the introduction. I would like to start by introducing the fact that nowadays we're using systems in the geomatics industry that are multi-sensor in nature, including sensors from the photogrammetric field, laser scanning, GNSS, and inertial. I'd like to define photogrammetry, which is the science and art of acquiring data from a normal 3D scene at a certain moment of time using a certain sensor on board a platform to acquire the data in the form of an image that when we take that back to the computers, we basically do the restitution necessary to produce that 3D scene again on our computers. Imaging sensors could be categorized either active, such as LiDAR or SAR, or passive, such as line scanners or flame cameras. Practically, direct georeferencing is a necessity for LiDAR, SAR, and line scanners, and it's an option for frame cameras. I'd like to start to address the applications by the non-mapping applications. If we look at the upper right corner here, this is a standard method of using photogrammetry in the automotive industry by Toyota, for example, a group of imaging sensors in order to do the necessary research and development activities for aerodynamics studies and crash tests, so as for the rest of vehicle manufacturers. And the bottom right corner here shows the way it's done, usually using targets on the vehicle and capture that in the form of photogrammetry to analyze the necessary R&D activities. In aerospace engineering, it's a daily activity to study the aerodynamics of aerospace vehicles. The picture on the right-hand side shows a test that was done in calibration of a group of organizations, including NASA, US Navy, FAA, and DLR. And he called it the pocket dot test because of the fact that they covered the entire body of this airborne vehicle with dots, and they analyzed the crash tests using photogrammetry. Medical engineering, MRI, is one of the applications, one of the examples of medical engineering use of photogrammetry, where this pod is full of sensors, photogrammetric sensors, to capture the data in both 3D and real time to produce that look of the MRI for diagnosis purposes. Back to the mapping applications. The number of applications in the photogrammetric business are actually endless, But we'll basically highlight the major ones, including airborne using manned or unmanned vehicles, mobile mapping using a group of sensors, again, LiDAR, imaging, GNSS inertial on board a vehicle to map the roads and infrastructure. Same nature of sensors are on board, typically nowadays on board indoor carts operating in an indoor environment to produce maps. And similar nature sensors are used in an integrated sensor environment on board a marine vessel for seafloor mapping. Mapping products, the typical ones are orthophotography, 3D topo maps, including contours, and triangulated irregular networks, including break lines, and the standard conventional 2D planimetric maps, including buildings and the road infrastructure and the facilities, amenities of our communities. LiDAR brought in the ability to analyze the structure and composition of various infrastructure utilities, such as the transmission lines, to analyze the sagging and so on. And this is a photorealistic 3D city model. As far as sensors are concerned, we have a category of large format cameras, and those are typically fully integrated, expensive sensors carrying on board a group of cameras, as you can see here, a group of lenses. And internally to the system, it includes typically a computer, an inertial measuring unit, and a GPS receiver, and for data processing, data storage, and so on. Nowadays, for the UAV industry, it's a lot more common to have medium format cameras and small format cameras, as well as spherical cameras. On the non-camera side of things, we have the LiDAR. We're showing here the Regal version or the Eluscan version. And those are examples of the hyperspectral, multispectral sensors and synthetic aperture radar. Data examples, we have the standard form of digital frame image or a group of video images. And as far as the LiDAR is concerned, this shot on the right-hand side is from an aerial LiDAR platform. And you can tell that you have all the types of details. You're looking at the street furniture and road markings. And this shot on the left-hand side is showing footage of LiDAR from a land vehicle. GNSS Revisited. GNSS includes GPS, GLONASS, BEODO, and Galileo. Nowadays, the autonomous positioning accuracy has come along really nicely down to a few meters, to be more specific, up to 3 meters. Relative positioning allows for centimeter level accuracy, as you already know, using some sort of aiding or augmentation mechanism, such as base stations, cores, IGS, or real-time post-processing VRS. In the UAV industry, it comes down to using either RTK, which is the abbreviation of real-time kinematic, or post-processed kinematic. It comes down to your application. What are you after? So if you're after high-precision mapping, you're much better off with post-processed kinematic. And that allows you to take the data back to the office and you integrate with other technologies such as inertial, which is very important fact to be able to have unlimited integration capabilities, including loosely coupled and tightly coupled and so on. And you're not actually bound by any limits for a radio link. Yet, if your application necessitates having on-time products such as the emergency response, reconnaissance, surveillance, you're much better off using the RTK, and then you are limited, you have some limitations, yet you are within a reasonable accuracy for that on-time or real-time application. When you integrate GNSS with inertial, you end up with full 6 degrees of freedom at a very high rate, typically 200 Hertz. And that allows for basically integrating the two streams of two technologies, and that is best done at the tightly coupled level in airborne environment. I'd like to define georeferencing now. Your house zip code or postal code is a unique identifier of where it is with respect to your city, and that's a piece of georeferencing information. And this is exactly how we define the georeferencing of an image with respect to a mapping frame of reference. And that image could be either a frame image or a scan by laser, SAR, or a line scanner. And once you define the relationship between that image with respect to a mapping frame of a reference identified or defined by local mapping agencies, typically, you have the georeferencing taken care of. Then you could actually produce mapping products from that image. We do that using two technologies. First one is called area triangulation, a solid technology inherited from the 50s, 60s, and it came along very well, actually, for a few decades, and it became the standard operating procedure in the 90s. And that is actually done by establishing something called ground control points. And GCPs are simply some points on the ground that you survey in using conventional static GPS or some conventional survey methods. And then you measure the locations on the imagery, and in a large least squares adjustment filter, you compute that georeferencing, which is the position of your image with respect to the mapping frame of reference, as well as the orientation of that image with respect to the mapping frame of reference, called area triangulation. Once you establish that relationship, you'll be able to produce the mapping products. Back in the 90s, direct georeferencing came out, which actually allows for measuring control up in the air, where you measure the camera position and orientation with respect to your mapping frame of reference using GNSS inertial. Since you are flying free like a bird and you do the control measurement up in the air, basically you need to do some proper quality control of the data to make sure that you're putting the map that you're producing in the right spot. And then you produce the maps. And there's no need for any ground control points whatsoever in theory. This is just a look of the ground control points. We typically survey them after we spray them on the ground if before flying, or after flying, we could just identify them from the imagery and go out and survey them in. The typical computer vision way of defining the coordinate system of an image is having the coordinate system origin sitting at the upper left corner pixel, and then you count the pixels to figure out the location of your target on the image. Now, in the mapping industry, we actually use the center, geometric center, as the origin of our coordinate system. But what happens in reality is that the footprint of your optical axis of the lens doesn't necessarily happen to be at this geometric center. It usually is somewhere else. We call it principal point, and that actually ends up defining those two little shifts, and those are considered calibration parameters. They look so simple, yet once you start to fly in different directions, they kind of pollute the results, and you need to be calibrated and taken care of properly. So as the lens, typically a lens is a compound lens as opposed to a single lens. And because of the fact that those lenses come with their own imperfections, we end up with something called lens distortion that actually makes the look of the image of a point somewhere else. And that deviation or discrepancy is called lens distortion, and it needs to be taken care of as well in the form of calibration. The way area triangulation, the conventional method, takes care of that is actually a method of building a block of images. And this is a flight line, for example. We have an 80% and 80% overlap and side lap as a necessity nowadays in the UAV industry. And we measure a lot of points on the images. If you're passing from one image to the next, we call them pass. If you're tying two consecutive strips of images, we call them tie points. And then you measure those triangular indicators of ground control points, an abundance of them, and end up with a large least squares filter to adjust the data and come up with the necessary georeferencing parameters, which would then allow you to do map production. In non-urban environments, such as the deserts and rural environment, having tie points and pass points is kind of challenging, and self-calibration is always necessary to take care of the caveats that we discussed earlier. In direct georeferencing case, you're actually measuring everything up in the air, and as a result, you end up with no necessity whatsoever of having that kind of block geometry. And it is a necessity to have direct georeferencing with the LiDAR, SAR, and scanning sensors, and for frame imaging, it's an option. This is a further insight into the direct georeferencing, where the red color code here represents calibrated parameters such as those lever arms or distances between different sensors on board, and those little matrices representing the orientation offsets, again, calibration parameter. And the blue ones are basically the measured quantities. For example, a Boresight is defined as the mounting angles of an IMU with respect to a camera. So those little differences or orientation offsets between the IMU frame of reference and the camera frame of reference, typically mathematically modeled in the form of direction cosine matrices, and that needs to be taken care of as a calibration parameter. Looking at a simplified error budget here, what we're looking at is a group of sensors embedded into one system, and you need to analyze the effect or the influence of each of these sensors on the final mapping product accuracy, such as GNSS inertial, geometric stability, camera interior geometry, such as the focal length, principal point offsets, and lens distortions, and many other factors. Now, looking at that map here of error budget, it kind of looks that the direct georeferencing is a complex theory and a complex mechanism. Yes, it is. And that actually was a challenge back in the 90s. For the last 2 decades, the development has actually reached to a point where every single parameter of these has been modeled properly in the software environment, which allowed us to do corridor mapping, stereo pairs of images, and single images with no need whatsoever to do blocks of photography. This is how we do quality control. We go and fly like a bird, single flight lines, do corridor mapping, but then we select an area to do the necessary quality control, and then go fly everywhere else in form of single flight lines and such. So this is basically a summary of the direct georeferencing versus area triangulation that I addressed before for your reference at your leisure. And I would like to address here a quick example flown by Avion using a micro drone MD4-1000 that had a Sony A7R camera equipped with APX-15 and a 35mm Zeiss lens to map the Frere Dam out in Quebec, Canada, which is a corridor mapping project with only access to have 5 ground control points on the sides of the dam, because the dam structure itself didn't allow for establishing ground control. What we ended up with, using industry standard software packages such as POSPAC and Info, is producing a 1 centimeter GSD orthomosaic, and that's what you're looking at here. And what we're looking at is the accuracy of that orthomosaic using those ground control points as checkpoints. And we're looking at here 3.5 centimeter and 1.5 centimeter in easting and northing respectively, which implies 3.5 pixels and 1.5 pixels in the horizontal direction. So basically, we did one of the most challenging applications in the mapping industry, which is corridor mapping, with no ground control points, with just one drone using the UAV direct georeferencing technology to produce a mapping product that wasn't possible to produce a decade ago. And that concludes my presentation. Thank you for your attention, and back to you, Demos.
Thank you, Mohammed. All right, so let's move on to our next panelist, and then we'll move on to a Q&A session after that. So our next panelist is Mike Hogan, who is the Business Development Manager for Avion, a North American-based company that provides professional UAS services for industrial applications. Prior to joining Avion, he was a member of the Royal Canadian Air Force for 22 years, where he was employed as an airfield, geomatics, and intelligence officer. He received his Bachelor's of Engineering and Civil Engineering from the Royal Military College of Canada, and a Master's of Engineering in Geodesy and Geomatics from the University of New Brunswick. Glad you could join us, Mike, and I'll turn it over to you.
Thank you very much, Demos. It's really good to be here, and I'm really interested into the discussions that are coming up. Just to kick off, just a little bit about our company. I'll push on a bit further because I think it's important to know that we're offering and working with 2 different manufacturers, Microdrones and Dell AirTech. Our main focus right now is really the surveying and mapping markets, and with these 2 companies we can provide very interesting solutions that can probably meet a lot of the different mapping work that's out there. just to kind of give an idea of the fleets that are what's available in the fleet is you have systems that are from various weights of less than 2 kilograms all the way up to systems that weigh potentially up to 25 kilograms that can fly, less than 30 minutes all the way up to, over 3.5 hours, depending on the configuration from there. And just to note, for these systems, except for the MD4-200, all the other systems have already been integrated with the direct georeferencing capability, so which allows for that corridor type mapping. And as the market expands and the regulations expand in North America, to be able to do that type of work. So traditionally, the options for collecting your geospatial data have been focused either from an aerial perspective or from a surveyor on the ground. I'm not going to necessarily talk about the mobile mapping piece here. I'm just talking about specific areas that we look at. So within there, the options from clients to be able to choose that is that you have very little overlap, and there might be a big gap in there where an area is too small really to collect, or it's too expensive for that small area for an aircraft, or it's the same thing, it's too big for surveyors to go and do it to collect that area. So this is where small UAVs are really making their way into the market space, where they can bridge that gap and allow it to do it. I don't call, these are really complementary systems working together. One system can't do it all from there. So really what they offer, and I think has to be highlighted in looking at it, is efficiency. And the prime example I talk about there is only collecting the data that you need to collect for a specific operation or time frame. I had a client that talked to me that said, Mike, can you map or provide an elevation model of these 60 kilometers? And I said to him, why do you want to map 60 kilometers? He says, well, because that's what I did last year, and that's kind of the best way to do it. I said, what are you going to use this year? He says, I'm going to do 2 or 3 kilometers. I said, well, let's just map that 2 or 3 kilometers for you and look at that. So that's where I think UAVs provide that efficiency. From a safety perspective, we're now eliminating someone actually walking on the ground or having to access potentially a dangerous construction site, or as alluded to on the fire dam, actually accessing a site that they don't have. So safety is a big factor in the whole piece. Flexibility, as we move forward, the developments more and more with the sensors, we're going to have multiple sensors on board to collect multiple data sets to support the requirements of our clients moving forward. Economical, I've alluded to that already a little bit about only collecting what you need, but that's going to be a whole piece that adds it to the tool set, is being able to provide a competitive advantage to your clients. In the end, the biggest one, I think, is the repeatability. The ability to collect data for a specific site pretty much whenever you want to collect it. So you can imagine, in the pre-planning stages of a project, throughout the project cycle itself, and then doing the as-builts and the like from there. So that all these factors really mean greater access to geospatial data. I think it's going to really transform how clients demand and ask for products moving forward. So the big question is how do we take these systems, the professional systems, and really try and make them more efficient and more accurate. And what I'd like to describe next is the work that we've done with the MD4-1000 in integrating the direct georeferencing capability. With this what we've done is said we want to provide a solution that's been proven in manned aviation for over 20 years. The work has been done taking these boxes and GPS receivers and IMUs that used to weigh 20 or 30 pounds and have now been brought down to a weight that's actually quite impressive. If you look here, the 220 channel GNSS receiver and calibrated IMU weighs about 60 grams. That's pretty impressive. We add that combined with a dual frequency survey grade GPS antenna, and then we're taking our camera, which is an off-the-shelf camera, a 42 megapixel camera that's been calibrated, okay, and we're providing a timing factor in there, so we're getting the accurate timing to allow us to bring that system together and to do what Mohammed explained in the direct georeferencing solution. And really, the big concern with UAVs is actually trying to get that accurate payload down to make sure that we can be effective in our mission accomplishments. So at this point, I'd like to pass it back to Damaz, and we can I'll talk further afterwards.
All right, thank you, Mike. All right, so we are at the point now where we have a few minutes here to ask questions of our panelists. So, and please send in the questions. We've got questions coming in already. So if you have any questions, please, again, send them to us and we'll ask the panelists. So this first question is for you, Mohammed, and if the others want to pipe in after Mohammed answers, please do so. One of our listeners says, I have found oblique images improve accuracy in mapping, and I use ground control, GCPS. Do you sometimes use that, and can you say something about that?
Actually, I've been involved in the development of integrated sensors, including oblique images, since the mid-90s. So I've done quite a bit of those real-world tests and flights for map production purposes. So what we've learned over the years is that oblique images, they kind of need special attention on the georeferencing side of things. Yet we ended up with producing very high accuracy results because of the fact of the geometrical influence of the oblique images, particularly on the height or the elevation component of ground objects. But yet we don't now use ground control points. So basically, Michael's application obviously necessitates ground control points for a certain reason. But at the moment, ground control points are not necessary once you have the proper professional grade GNSS inertial involved in the mix.
All right, Trond or any of our panelists, do you want anything to add to that, or? All right, I guess not. All right, so the next question, let's see, I will, I'll pose this one to you, Trond. I know I haven't introduced you yet, but I'll give it to you. And if others want to pipe in an answer, that's okay as well. Which sensor should I spend most effort on, the GPS or the inertial or anything else, to get good georeferencing and mapping performance? Can you say something about that?
Yes, it all depends on your application, but our system is a push broom scanner, and usually hyperspectral systems are push broom scanners. So the inertial is extremely important for you to get a rectified image that looks good. And if your application is just flying a few lines and doing research on those lines, you probably won't need very accurate GPS. But if you want to have really great performance, you need both good GPS and inertial. But I would say that inertial is the most important for these scanners.
Okay. Any of our other panelists want to add to that?
Just a quick input. To just add to what Trond mentioned, that inertial is a necessity in the case of line scanners, LiDAR, and centric aperture radar. In the case of frame cameras, it's not a necessity, it's an option, but it actually facilitates greater efficiency as well as it allows for high precision mapping.
All right, thank you. Let's see, this one is for you, Mike, and I'm going to paraphrase the question here. And the question is, what are the, I guess, the trade-offs between using UAVs versus manned aircraft for doing these kind of mapping applications? Any general guidance along those lines?
Yeah, I think that's a good question. I get a lot, and I have discussions with people. Everybody wants one tool to do the job, the multi-tool. In general, I found that you need a full toolbox. You need a hammer when there's a nail, and you need a screwdriver when there's screws to do there. So I think that similar with that both fixed wing and multi-rotor have their places to do it. But generally, the general trade-offs are obviously you can cover larger areas, longer distances with fixed wing aircraft. With the multi-rotor, you can generally get heavier payloads on board, but that's changing depending on the system. And plus your takeoff and landing is quite a bit less with multi-rotor. So those are kind of the general pieces. And I think, specifically to the direct georeferencing that goes, you're with multi-rotor, you have more control over the roll and pitch and being able to accommodate, to take advantage of that. But again, both of them, I look at them as essential tools, and having the right tool for the job is important.
Joe, is there anything you want to add to that by any chance, or did Mike get it all?
No, I think Mike summed it up quite nicely, and that's really one of the challenges today is which tool do I need to do the job efficiency? And I think that is a lot of the confusion that we see today in the UAV segment is what is the best method to collect my geospatial data? And I think we are slowly converging to the right tool, the right platform for the job, but there certainly is a lot of work that still needs to be done.
All right, so let me ask one more question before we move on with the second half of our webinar. And this one I'll direct at you, Mohammed, but again, everyone else chime in if you have inputs on it. And it is, without ground control points, how can you match up data accurately from different flights and from nearby projects?
As mentioned during my presentation, the control is measured by GPS inertial up in the air. And typically that alleviates our adjustment from any need of ground control points. But in the case of Gary's application, where the actual question was to have different flights or nearby projects. So if there are different projects in the proximity of each other and you'd like to overlap these, it would be a good idea to have a ground control point to make sure that you're putting your map in the right spot, but not an abundance of them. One or two to make sure that we can take care of any datum deficiencies or calibrate the datums in nearby projects or flown from different days.
Thank you very much, Mohammed. Let's move on to the second half of our webinar, but there are a lot of questions coming in, and please keep them coming in, and we'll have a second Q&A at the end where you can ask more questions. But let's start with a poll before we move on. So Laurie, can you put up the second poll question?
Sure. Coming up on everyone's screen, you should see that second poll. And in this case, we are asking you on your honor system to select your top 2 options. The question is, the accuracy of which PNT measurement is most important for direct georeferencing? So go ahead and give us your top 2 choices. Accurate position, accurate attitude, sensor geometric accuracy, accurate time tagging. Okay, looks like front runner here is 76% saying accurate position, with 49% saying accurate attitude, 40% sensor geometric accuracy, and 29% accurate time tagging. Demos, any thoughts on these responses?
Well, time tagging didn't get a lot of votes, but sit tight, and when Tron comes up, you will see how time tagging could also be a very important thing to be careful about. So that's coming. So that's a nice poll. Breakdown. All right, so let's move on to the second half, and I'm going to hand it over to Mike again, and he's going to tell us a little bit more about work they've done. So, Mike.
Okay, thanks again. What I'd like to go into now is really where we can look at the potential savings, where the efficiencies and accuracies come into play. And I kind of broke it down a few kind of general headings for the different parts of any kind of mapping mission, either project planning, typically GCP layout, installation, the flight time that's involved in conducting the mission, and probably the biggest part in there is the data processing after the fact, because it's potentially most of the work. Some of the other opportunities I'll elaborate a bit more on as I go forward is really the kind of the corridor mapping, those that can really be used with this type of capability, or mapping the inaccessible areas by foot or by vehicle from there. So what I'd like to do is use a sample area just to kind of give you an idea, 500 meter by 500 meter, which isn't unrealistic for a small UAV. There are areas where, gathering the data could be very difficult, but this is could be a normal, typical area to collect. A flying height of 120 meters or 400 feet, which now in the US, the FAA just boosted up the blanket COA that comes out with the exemptions to 400 feet, so that's good. For multi-rotors, an average speed of about 6 meters per second is pretty good, using a Sony camera and a front lap of 80%. Now I'll go into a little bit about the side lap and the options that we can go through there depending on the system. So on the left is what we use, the high precision, the direct georeference system with the MB4-1000. On the right is, without that capability put in. So with normal aero triangulation on the right, we would have to have a higher side lap involved with the mission. In addition, we'd have to install the ground control points. On the left-hand side, because of the direct georeferencing, we can limit the side lap that's involved down to 40%. And to give you an idea of the savings, for flight time, you're looking at 50 minutes versus 35 minutes. So what in this case is you're done in half the time, or you can potentially cover double the area for mapping type missions. In addition to that, the number of photos is less also, for which will save time in the post-processing from there. So just to kind of break down, looking at that specific scenario, maybe where some time savings could be, some efficiencies could be built in. So the project planning, there could be a little bit, really that's normal for any project that you have. The GCP layout in this case, you could about 2 hours, compared for the direct georeferencing, you would not have to lay those out for that. Flight time, as we already discussed, there's a considerable savings there. And then the data processing, in this case, we looked at about 12 hours for processing through the aerial triangulation, and the 600 images compared to 4 hours. So just kind of looking at the difference at the end, you could save potentially up to about 10 hours for this small case or test case study. So I want to go a little bit more into what Mohammed talked to about the one mapping job that was conducted was this dam. Now it's a very interesting case because it was not accessible, and as you can see, there were large concrete walls on either side of the dam where our operator actually had to fly the system, operate from a ladder. Was no issues there, and also was over a river, so it was water, which made things more difficult even in the processing piece from there. But our customers' requirements were really to get an orthomosaic and a digital surface model, sub-meter, and so we endeavored into doing that. So this mission was actually conducted over 11 flights. One of the first flights was the nadir flight, using the direct georeferencing, which is illustrated in red here. But in addition to that, there were flights done on either side of the bridge, pointing at 90 degrees and 45 degrees. And also at the end, there's a metal structure that was mapped in order to get that imagery to help generate the products out of that. So looking at the results, and they already alluded to a little bit, but we were able to achieve that 4 centimeter accuracy in the X and Y, and less than 10 centimeters in the Z, which I think it was very important, and it met the client's requirements for this job. But as you can see in the illustrations below are some of the cloud, the 3D clouds that are generated from the structure that allowed them to move forward in the redesign or modifications they're going to make to the structure. And this is something that they could have never done. They tried to do it with a boat in the past, and really it wasn't achievable using someone on the structure, nor flying with an aircraft from there. So really, in summary, that the MD4 1000 with the high precision capability provides that opportunity for time and money savings in operations, and it is it's using proven industry standard, proven technology, proven methodologies, proven software to meet the accuracies that are demanded throughout that workflow. Moving forward, the development is not going to slow down. We're coming out with a larger system, over a 3 kilogram payload. So taking that direct georeferencing capability and applying different sensors, LiDAR, hyperspectral sensors, etc., and then moving into the beyond visual line of sight mapping piece from there will really make things interesting moving forward. Thank you very much. Over to you, Tomas.
All right, thank you, Mike. All right, so let me introduce our fourth and last panelist, who is Trond Luki, Trond holds a Master of Science, Master of Technology in the field of photonics, and a master's thesis in hyperspectral imaging from NTNU and NEO in 2003. He started working at NEO as a research scientist in 2003 and became a senior research scientist, and is currently the CTO of the hyperspectral group at NEO. He has worked continuously with all aspects of hyperspectral imaging systems, development, optics, electronics, simulations, calibrations, everything, all the way from concept studies through prototypes and products. And he will tell us some of the work they've been doing in that area. Trond?
Thank you for that, demos. I will start to say a few words about hyperspectral imaging in general. So, hyperspectral imaging is combining imaging and spectrometry. So, in every pixel in your image, you will not only get your 3 usual colors, red, green, and blue. You will get several hundreds bands or colors continuously within a spectral range. Usually the sensors are like line scanner, we call it push broom scanner. So you are taking or acquiring a very narrow strip on the ground with all spectral information at one time. And then you build up the scene by either moving the camera or the scene. I usually like to use this example when describing what hyperspectral imaging is. Here you have 4 plants. One of them are artificial or a plastic plant. We also hidden a Lego person in there. So if you look at the basic, a normal monochromatic camera, it's a grayscale image basically you're getting for that camera. You will see energy from 400 to up to 800 nanometers for a very wide range. Multispectral cameras, including RGB cameras, have from 3 to 10 bands or color. Those are usually very wide and are covering from 3 to 10 spectral channels. Hyperspectral goes from tens to hundreds, very narrow bands, and will then give you a spectra basically from your scene. So using that spectral information, you can do a lot of stuff. Here's just an example where you just look at similar spectra in the image and classify them in different groups. And you can easily see that the plastic plants is easy to detect because it doesn't have the chlorophyll edge. You can also look for spectra that are different, that are not part of the common spectra in there, and like anomaly detection. And then you can see the Lego person is really lighting up. So hyperspectral imaging has endless applications. So I'll just mention a few. So for military, it's like target detection and identification, surveillance, search and rescue, forest mapping, you have classification, forest health monitoring, precision farming, growth monitoring, yield prediction, you have mineral mapping, environmental impact around mining areas, algae blooming, oil spill detection, land and sea monitoring, land use monitoring, and urban planning and management. So here's just a few classification results using our sensors. So I'm here to present also our new truly scientific grade hyperspectral solution. It's called Mjolnir 1024. I will come back to what I mean by scientific grade hyperspectral. Here's just a small video from actually 3 days ago in Toulouse, where we had the demoing the hyperspectral solution. This uses a drone also from a Norwegian company called Camflight. So sorry for the stuttering of the video, but yeah. Yeah, I'll move on. Inside the blue box here, you have the hyperspectral camera that weighs 1.4 kilos. You have a Pico ITX i7 computer, quite powerful computer. You have SSD storage, you have controller cards, mechanical shutter for dark current, you have frequency divisor, and you have the applanix APX15 UAV. I'll go through some of the key specifications. You have the spectral range for this system is from 400 to 1000 nanometers. It has 1024 spatial pixels, 200 bands, 3 nanometer bandwidth. It's a f1.8 system with 20 degrees field of view. The noise floor of this one, it uses one of the newest detector just out before Christmas. It has 2.34 electrons noise floor, dynamic range of 4400 and peak SNR at 180. It can run at 285 frames per second, and it weighs 4.5 kilos. When I said truly scientific instrument, I mean that the quality of the spectra in each pixel has to be very good. It has to be low stray light, has to be low spectral and spatial misregistration. We deliver with every camera a test report, of course, which tells you all the specs on your camera. You get noise, SNR, NER, the stray light, spectral and spatial resolution, the field of view, and all the misregistration, keystone and smile, and so on. Together with the test report, of course, we are doing the calibration of the instruments in our lab. So we do the radiometric calibration, the spectral calibration, and also for the georeferencing part, it's extremely important that you do a very accurate geometric calibration. So you're basically mapping the pointing angle of each pixel. At that time, you are mapping this pointing angle with reference to the camera. I will come back to how to do it reference to the IMU. So to get good georeferencing result, you need a good INS solution. We checked out 7 different solutions, and we came up with the APX15 UAV being the best compromise between weight, size, price, and performance. Saying that, Mjolnir will also work with any external INS as long as it has an event input. So if you have already a navigation system on your IMU or on your UAV. You also need a good antenna. There are many good antennas out there, but some of them suppresses the noise, the PWM noise from these multi-rotors better than others on the L2 frequency. So we ended up with a good one, and we also, by adding a 10 centimeter aluminum plate, like a grounding plane under the antenna, that reduced the noise even further. Yeah, now the timing of airframe. So I would say that maybe at least from hyperspectral manufacturing point of view, this is the most important thing. You can have a low-end IMU costing 1,000 euros, or you can have a 200,000 euro system. But if your timing of every frame is not accurate, you will not get any good georeferencing results. So the way we do it, we have a controller card, which is having a frequency generator, which is triggering the detector. The start of acquisition doesn't start exactly at the trigger. So we use the strobe signal from the detector itself and send that back to the controller card. The controller cards divide down this frequency by a factor 8 for the APX solution and send that into the APX solution to be timed on the event input. The reason that we are dividing it down by 8 is that the APX has 50 Hertz maximum frequency on the event. So we have to always be underneath this limit because we can trigger it at 280 frames per second. And all navigation systems out there have limitations of how fast they can time events. For the APX system, it has a better than 1 microsecond accuracy of the timing, which is very good. You here see some example of the trigger and the strobe being generated from the detector and the event being sent into the APX system for timing. Having all the hardwares necessary to get good georeferencing results, you also need to, because you are usually limited on flying time, so you need to align the INS very fast. We do this by flying a straight line for 30 seconds and then doing an 8. I recently also learned that to align the heading, you should have some fast acceleration and deaccelerations. And here is just a video showing you a flight plan from our flight planning system when we are actually flying. Yeah. Also, what Mohammed mentioned, the Boresight is extremely important. So to do the direct georeferencing, you need to know the offset between your camera system, coordinate system, and your IMU. So you only do this once, as long as your IMU is mounted rigidly to your camera and is not moved. So I would say that you need at least 20 GCPs on the ground in one flight line. And once you have these offsets, you can do direct georeferencing without GCPs. Yeah, so looking at the overall accuracies, georeferencing accuracies, if you look at the pixel size of the Mjolnir system, it has 0.02 degrees. For post-processed INS data, we can achieve 0.025 degrees accuracy in roll and pitch. That's like 25% more than a pixel. On a 100-meter flight, you have pixel size 3.4 centimeters. So with post-processed GPS data, you can achieve down to 2 centimeter absolute accuracy. So the absolute errors are on a pixel level, which I think is very good. Yeah, like I said, the system is a generic system, so but we deliver it with the APX15 INS and with a CamFlight UAV. It can also work with any other navigation system as long as it has an event input. It can also work on any other UAVs as long as it can lift the weight. But you have to take care of course, mounting the IMU rigidly to the camera. That's very important. The battery is galvanically isolated from the electronics inside Mjolnir, so it can withstand a lot of noise on the input. It can go from 9 to 32 volts input, and also by removing the ripple on the voltage, you can increase the lifespan of your LiPo batteries. yeah, just briefly mention that you have, of course, a lot of link options. You can use the TCP/IP link, HD video link, plus serial link, or only serial link. So a lot of UAVs out there have serial pass-through on their links already. So you can use that as a minimum requirement to control the system. So if you use a TCP/IP video link or HD TCP/IP link or an HD video link, you can get basically the mission computer down to your ground station, and then you will see this window. You will see the control of the camera. You will see a waterfall preview here on the left, which starts showing you 3 selected bands from the 200 bands. You will get some status messages, a real-time video feed. Here you have the INS information, real-time XYZ roll pitch heading with the standard deviation. You will on the left here see the events coming, so you can see that the timing is done correctly. You have exposure control, and you can see the link status, the battery monitoring, and temperature. And some special UAV commands on the left here. Looking at the data processing chain, of what I call post-processing chain, but from a classification end, it's probably called pre-processing. But it's you have the high-specs air, that's the software in the mission computer, which is capturing the raw data. So you have a big binary file with the raw data, and you have a binary metadata in the beginning containing all the calibration information and the dark current, which is always acquired when you're not acquiring a background. You have a mechanical shutter, which is closing the aperture. High-specs RAD, it's a software for radiometric calibration. So I will come back to that in the next slide, but this is converting from raw to at sensor radians. When you have at sensor radians data, you are ready to rectify the data. So, but to rectify it, you need to know the INS data for every frame. And a hyperspectral image can be 100,000 frames. So for every of these frames, that can be 280 times per second, you need to know the position X, Y, Z, roll pitch heading. So to do that, you get the data from the APX, the raw GPS IMU data, you process it in pulseback. Out you get 200 hertz INS data and an event file. Together with the session log file, you will actually be able to resample those INS data and get one file per image containing XYZ roll pitch heading for every frame. Then you're ready to do the rectification in Parch. So Parch is one of the software you can use. But to do the rectification, you need to have a sensor model. That's the geometric characterization I talked about earlier, and a good digital elevation model. So if you don't have, if you're looking at absolute good results, you have to have also a good digital elevation model. After Parch, you will have an auto-rectified radiance image, and you will also, or if you want to have auto-rectified reflectance, you can use ATCO 4. Yes, and then back to high-specs RAD. So in high-specs RAD, it's converting the raw data to at sensor radiance data. So the first thing it does, it's a radiometric calibration. So it's removing the background, fixing the non-uniformities on the pixel level, and then you have at sensor radiance data, but with some distortions. The next step is to resample the spatial and spectral distortions, the SMILE and keystone. After this is done, you have another level of data, and the last level, the last step is basically to compensate for the QE, that is quantum efficiency, that is changing based on the temperature on the FPA. That's the detector temperature. So yeah, that's the last stage, and at the end, you have at sensor radiance that is traceable in PTB standard. Quickly mention something about the CamFlight UAV. It has 8.3 kilos payload. It can fly for 25 to 30 minutes with 6 kilos. It can fly for more than 50 minutes with 1.5 kilos. It has a Campos M positioning system, ATK link to the base station, post-processing and position is possible, photogrammetry without GCPs. Autopilot is from Lockheed Martin, so for high precision flights, and it has a 15 square meter rescue parachutes. And the software called Virtual Cockpit is controlling the UAV and doing the flight planning. Here's a graphical user interface from the virtual cockpit, just showing you how to do the flight planning. You can do automatic takeoff and automatic operation and automatic landing. You can also control the hyperspectral system directly, so you don't have to do anything during the flight. I briefly want to mention here at the end our real-time georeferencing software. It's a software that we developed together with the Norwegian Defence Establishment in 2013. It can do real-time georeferencing and visualization and do some real-time classifications. It can be an anomaly detection, PCA, or MNF. In the long run, we want to implement custom algorithms to make real-time classified maps, real-time target detection, or real-time indices maps. The software has been tested successfully on a campaign in 2013 and been operated continuously since then. So our goal is to include this software in the UAV package. So here is just a little video showing you how it works. We are here flying, it's on an aircraft, and we are flying over Oslo. And when we are flying, the system is rolling and pitching, and you will see that very soon that you have large roll movements, but you can see that the buildings are being rectified and georeferenced very accurately. Yeah, conclusion. So the Mjolnir 1034 is a state-of-the-art and a scientific-grade hyperspectral imaging system that's designed for UAVs, and is based on our more than 20 years experience in the hyperspectral imaging. And high quality components and rigorous testing ensures optimal performance. We will have shortly a demo data set available, so just contact me and I will send you some FTP information. Thank you, and back to you, Demos.
Thank you, Trond. All right, so before we move on to our final Q&A session, a couple of things about the next steps. First of all, the PDF of this presentation and a list of resources will be available at the Inside GNSS website after this webinar. And we've also put up contact information for Inside GNSS, applanix, and our panelists as well for further contact in the future. With that, I would say let's move on to our final Q&A sessions. So let's see, let me start with the first question. This one is for you, Mike, and it was about the bridge data that you presented. What software was used to do that processing?
Yeah, what we used for the post-processing the GPS and IMU data was the post-pack UAV. And once we had all that information, from the post-pack, it was processed in info from Trimble.
All right, thanks, Mike. Let's see, next question. Joe, let me pitch this one at you. Do you expect the cost of the total UAV systems to come down in the future? And can you say anything about the trade-off of things that are on board, components that cost a lot, et cetera, along those lines?
I think it's a really good question, but I also think we need to step back and look a little bit bigger at the picture. So really what we're trying to do is put the pixel at the right location on the ground for the most cost-effective way. And whether you use a UAV, whether you use a mobile vehicle, whether you use a manned platform, what's going to come out of that is a cost. And so I think what we're going to see over time is the total solutions are going to be tailored for the value they bring to collecting that geospatial data. So, as Mike mentioned today, one of the big advantages of adding direct referencing to UAV platforms is to increase their efficiency. And so some people get hung up on the capital equipment cost, but if you actually look at your total cost of ownership and your cost of actually doing the missions, by just being able to eliminate the number of GCPs you need to survey, or the time it takes processing, those savings become much higher and quickly pay for the higher capital costs. So I think it's something that will evolve over time, and it's not much different than 20 years ago when we first introduced technology like this for aerial fin counters. It evolved, and the best solutions came out that were the most productive, that allowed people to get the data they wanted at the right price.
All right. Thanks. Let's see, next question. This one is going to be for you, Mohammed. And let's see, which one do I, which question do I want to pitch for you? So, all right. So, can you speak to the process of co-aligning, co-mount cameras and the vehicle and alignment of the Boresight? Can you say a little bit more about the process that's used for doing the alignments?
This is actually a very good question because there are many products out there that include a group of cameras, not just one camera, and embedded GNSS inertial. The standard way of operation in that domain is to actually calibrate the bore sights of each camera with respect to the IMU. And there are commercial softwares available out there for the last decade to take that data in and produce the individual bore sight alignment from each camera with respect to the IMU.
All right. Trond, do you want to add something to that, or Mike? Or I guess not. All right. Let's move on. Next question. This one is for you, Trond, and it's about the coverage of the hyperspectral cameras in one flight. What kind of area can you cover with in a single flight with what you talked about?
Yeah, that's also a good question and a very hard question to answer because it depends a lot on how high you're flying, of course, what requirements you have, what kind of pixel size do you need of your end product. So you are flying, of course, you can run the speed of the system can be 285 frames per second. So if you're flying at 100 meters, for example, you will have 3.4 centimeters pixel size, and that gives you about that means that you can fly 10 meters per second with that speed. Saying that, you also need to take into consideration the light level. So if you don't have direct sun, for example, 285 frames per second will be basically you will be running the sensor at a lower exposure time, so you won't get your best dynamic range out of the images. So it's all a compromise that you have to take into account when you're flying and when you are doing the flight planning. So yeah.
All right, Mohammed or Mike, anything you want to add to that, or?
No, but I think it's a good point. It's the planning and it goes into the mission. It's, you know, a lot of times it's not just an easy button. A lot of the considerations that need to go in are the same things that go into the normal planning that we see for these type of sensors on manned aircraft.
All right. So let's see. This one is for you, Mike, then. Do you think the UAV-based mapping and surveying solutions will replace the human-based ground survey for a lot of these applications, or is this another one of those "it depends" type of a question?
I'll say, yeah, the drones are going to replace all the humans, and that'll be that. But no, I think the reality is it's a question of the situation. You know, I think they're really complementary. You know, depending on the job and using the right tool. There's always you're gonna need your options in doing that.
Okay. Let's see. Next question. This one is for you, Mohammed. Let's see, and the question is: do you require a DEM model as an input for your direct georeferencing algorithms?
It's a very good question. Actually, the only time we require a digital vision model is when we produce ortho photos. And that the way it works is that you end up with individual images directly georeferenced by GNSS inertial, and you add the digital vision model to produce an ortho photo. But if you're operating in any stereoscopic or like strip photography or dual images, you don't need digital vision model because it's embedded in the process of stereoscopic photogrammetry.
Okay. Let's see. All right, so next question is for Trond. Should hyperspectral images be orthorectified with the highest hit DEM at the same resolution, or a bare earth DEM?
Yeah, no, that's again also depending on the usage of the application. But for example, this Parch software contains the detail 2 of the whole world, which is a very coarse stem, but it could easily be used with a decent result on your accuracies or your rectification. But again, if you need on a pixel level accuracy and you want to fly lines and you want to overlap them and have, like Mike said, ortho photo, then for sure you need a very accurate DEM as well. So then the combination of a LiDAR or stereo images together with a hyperspectral system is perfect for that purpose.
All right, thanks. Let's see, next question. Let me, this one I will pitch to you, Mohammed, and then if Mike or Trond could want to add to us, then add to it. But does inertial sensor have practical influence on position, or is it primarily the GPS that controls when it comes to the direct georeferencing that you're doing?
Actually, inertial has influence and contribution to both position and orientation coming out of GNSS inertial systems. There are 3 points to address here. Number one, the data frequency. The highest data frequency by GNSS nowadays is 20 hertz or 20 samples per second. So if you're flying 60 to 70 kilometers per hour, which is translated to 20 meters per second, GNSS will provide one position per meter, while the inertial has a typical frequency of 200 hertz, which is 10 times. So you will have one position every 10 centimeters. So a much higher interpolation, very accurate positioning for mapping purposes. The second influence actually is that if you lost GPS at any point in time, particularly if you have tightly coupled integrated, which is mostly the standard mechanism in all the commercial systems nowadays. So you have the inertial data to kick in to fill in the gaps of GPS. So whenever you lose satellites, if you are in a GNSS standalone mode, you lost everything. But if you have inertial integrated, then you're still okay, and you still have high positioning accuracy. The third item is actually that inertial produces much higher positioning accuracy over a short period of time, until the errors of inertial start to deviate a little bit, then GNSS kicks in. So during the time when you expose a camera, you end up with higher positioning accuracy from the inertial than that of the GPS. And that basically is all I have to say regarding that matter.
All right. Trond or Mike, do you want to add to that at all?
No, I think it was a very good answer.
Okay.
Can't add anymore.
All right. All right. So this one, I guess a couple of questions that come out under this one. So let me try to bundle them into one and try to paraphrase them. Is if GPS is momentarily unavailable, how does that affect the problem of mapping with respect to timing, with respect to positioning, attitude? Is that something you take into account, and how do you deal with it? So I'll start with Trond if you want to say something about that.
Yeah, for the timing, for example, it's not a very big deal, because when you lose the GPS lock, of course, you lose the sync between your local oscillator and your GPS time. But the drift in an oscillator in that time, let's say that time is 10 seconds, is very minimal. You're talking nanoseconds. And so time tagging wise, it's not a problem at all.
Okay. Mohammed or Mike, anything about not GPS being momentarily unavailable, or when it's not available, if you can do any of this stuff?
I could just add to Trond's explanation. In a geometric domain, as far as accuracy are concerned, the loss of GNSS data, either momentarily or for extended a few seconds or so, is a very typical thing in a real mapping environment. We see this every day in everyday aerial photography missions, and having inertial on board fills in the gap at all times.
Yeah, it's Joe here. I'd just like to add to that. One of the big advantages of post-processing is the ability to go both forward in time with their GPS inertial solution and reverse in time with the GNSS inertial solution. So what happens is, if you have an outage in your GPS, inertial fills in the gap quite nicely in the forward and reverse direction. You get kind of an averaging effect. So you actually get improved performance through post-processing through any outages.
All right. So along those lines, a question that just came in, and again, I'll start with Mike, but I mean, Joe or Trond, you could also say, is there any, for example, is there any advantages, or do you actually integrate some of this data with ground data that you get from the ground-based data? So Mike, I'll start with you and pitch it to the others as well.
Yeah, I think that's a key element in the whole piece is you are using data from a ground station at some point. Either it's a GPS receiver base station on site, or you have access to a network or data, or it's a pseudo type site from there. So it's a key part in the solution in the post-processing of the data.
Joe, do you want to add to that?
Yeah, I think one of the key factors with direct referencing, of course, is eliminating the need to use ground control points, but it doesn't eliminate the need to do quality control. So you will always still want to have ability to check your end products with a few ground control points. They're not used for the georeferencing per se, but they're used for the quality control process. So that doesn't go out the window. It's still baked in there.
Okay. Trond or Mohammed?
Yeah, for hyperspectral, of course, when you're talking about ground data, you can also aid the process of going from radiance data to reflectance data by having some ground measurement with a point spectrometer, for example. But that's not on the georeferencing side, just on the spectral integrity of your reflectance data.
Okay. So this one is for you, Trond. It's what characteristics should I be looking for when I purchase a camera for remote inspection applications? I guess this is a kind of a broad question, but can you say something about that?
Yeah, it's a very good question, and of course you have many different suppliers out there with a lot of them have the same specs, so you can have the pixel and the bands is of course some obvious to look at, but what is also extremely important is to ask for actually your distortions basically from your system, because as I mentioned in my presentation, you have keystone and smile, that's spectral and spatial distortions. So but if you have, for example, 50% keystone in your system, basically the quality of the spectra is very bad, because some of the bands will then be coming, or some of the spectral signature, or half of the spectral signature will be coming from the pixel next to it. So if you have two objects close to each other, it will be a very unphysical spectrum. So I always recommend that you ask the supplier when you're buying a hyperspectral camera to get basically a list of the key specifications together with a test report, for example, showing the actual specs on your system.
All right. Mike, do you want to add something to that about things that to look for when getting cameras, or any advice? Or
no, I think it's key, and in looking at when we're looking at these solutions, when we're talking about these professional solutions, these high accurate solutions, every part of the puzzle is important, and selecting the appropriate sensor is a key part of it. Fortunately, there's a few benefits we have, and we can look at some of the off-the-shelf sensors. Is a lot of times the flying height helps us out, where that propagation of air is maybe minimized, and we can look at maybe the off-the-shelf cameras, they're properly calibrated for some of those applications.
Mohammed here. I actually like the answers by Trond and Mike, but I have a little something to add, which is the geometric component stability of the cameras. If we're addressing high precision mapping, the quality of the mapping product is basically the accuracy of the weakest component in this whole puzzle, as Mike mentioned. So the weakest component, believe it or not, is usually on the side of the cameras. So the geometric stability is important, geometric accuracy important, and then doing the workflow properly takes care of those caveats once we have the right sensor, like the right camera sensor with the right professional grade, basically stable geometry.
Okay, so next question, it's a slight twist of this, and I'll pitch it to you, Mohammed, because kind of would be nice. I think it's a nice follow-on from what you just said. Can you give us some rules of thumb on the UAV state error which ones are important? What should we be looking for when attempting to do things like direct georeferencing?
Actually, as Mike put it very nicely, it's just like a big puzzle with a number of pieces of puzzle. And so to do professional grade mapping, you need professional grade sensor assembly. The GNSS inertial is practically the best alternative available nowadays. And the camera is an important sensor. But if you are addressing particularly the georeferencing, GNSS and inertial, you need both. And then the geometry will dictate the form of errors. But you will not be able to actually get a particular solution addressing one project or one application. The best way to approach this is to have a professional grade system coupled with the right camera to attend to the different application accuracy requirements.
All right, thanks. Trond, this one is for you. Is anyone able to use software to compare last week's multispectral imagery from crop to this week's imagery, or anything else with a precise overlay, and being able to detect differences and changes? Is that something that can be done?
Yeah, I guess I have to talk for our customers here, but yeah, I know this has been done, and of course it all depends on the accuracy of your, because you have to then convert to reflectance. If you have a radiance data, you can compare the spectra, but you can have different apertures from last week, or different atmosphere from last week, I mean. So then you have to convert to reflectance. And if you have good reflectance data, you can compare last week's with this week's for sure.
All right. Let's see, next question. I'll pitch this one to you, Mike, but I'm pretty sure all of you will have something to say about it. I mean, it's something that I've also wondered about. Taking into account that small UAS are very unstable, they vibrate, they shake. Are there any things we need to worry about when it comes to installing sensors? Is there any stabilization that has to be done? And what are the side effects of all of this?
Yeah, so far what we've done with the multi-rotor platform is one of the biggest factors in installing a mount is actually getting that isolation vibration in there. And so we've gone through trial and error to get that piece right. And the good thing about it is that we have an onboard, you know, the applanix APX15 provides that IMU to measure what that is, the vibration. So that helps us out. But as far as the mount itself, it's actually it's a nadir mount. You know, that we use for the process, because we can actually control the roll and pitch of the system quite well at the flying speeds we have there. I'm sure the other guys will provide more technical detail into that also.
Yeah, Trond here. I would say that for when you're flying in not very still or wind still weather, you would benefit from having at least a one-axis gimbal in the pitching direction, for example, because when you're flying, you will get some constant pitching and constant stretching of the pixels. So if you're not oversampling a lot, that means running the camera at a very much higher frequency than you're flying. You definitely will have very stretched pixels going back and forth over the same area when you're flying at low altitudes. So I will always recommend to have a gimbal, and if you have a 1 or 2 axis gimbal, of course that will add some weight. So it all depends on how, in what conditions you want to use your system, basically.
Okay, well, along those lines, so when you have a gimbal, now do you have to have a separate IMU on the gimbal to tell you where it is relative to the vehicle itself, or?
So I think I'll jump in on that one, because that is always one of the interesting challenges. I think we're going to see in the UAV market is exactly what happens in the manned platform market, that the use of gimbals to keep your sensor parallel to the ground is going to happen. And the benefits of that are, you know, controlled overlap and more efficient flying. The challenge, of course, is that when you want to use direct georeferencing, you want to measure very precisely the position orientation on the gimbal itself. So the inertial measurement unit or the APX15 in our case needs to be mounted with the sensor on the gimbal, and then you have the challenge of translating the positions from the antenna, which is not mounted on the gimbal, down to that. However, that can be done. It is a little more challenging, and one of the bigger challenges that most of the gimbals today don't output the relative orientation that you need to do that, but there are ways around that. So I predict, you know, in the near future, all these systems are going to be flying with active stabilization, which you can do quite well with the GPS inertial, just because it improves the efficiency.
All right, thanks. Unfortunately, we're running out of time, and there are more questions than that could be asked. So with that, I think we'll close the Q&A session for now. So with that, I think I'll hand it to you, Lori, to do the wrap-up.
All right, thanks so much, Demos. And it is about that time to wrap up. Before we do so, a few closing remarks from Joe Hutton of Trimble Applanix. Joe?
Well, thank you so much, everyone. I was very happy to participate in today's webinar. Mohammed, Mike, Tron, Damos, excellent job. I think from the level of questions we received, I think it's evident that there's a lot of questions about how UAVs can be used efficiently for mapping. I hope we managed to answer some of those today. And you know, as Lori said, please reach out to us if you have further questions. And thank you again. Thanks for everyone for taking time out of their busy days and participating. Back to you, Lori.
All right. And most importantly, thank you all as well for joining. This is Lori Dearman saying, hope we see you on the next one. Bye for now.